Hello and welcome to this Revision Monkey video on what's going to be in the 2022 exams. This video is for AQA Physics and it's for separate scientists only. So you might be called triple science in your school or separate science. And these are the pupils that do 1 hour and 45-minute papers at the end of the course. This video is for Physics Paper 1 and is for higher tier students. The topics that won't be assessed in this paper are current, potential difference and resistance, series and parallel circuits, domestic uses and safety, and that's in the electricity topic, particle model and pressure, atoms and isotopes, hazards and uses of radioactive emissions and of background radiation, and nuclear fission and nuclear fusion. The required practicals they've told us that will be in the paper are insulation and density of regular and irregular objects. Do have a look in the description because I'll put a link to a video for these required practicals only. The rest of this video will focus on the following topics that the exam board have told you will be the major focus of the exam, and those are energy changes in a system and the ways energy is stored before and after such changes, conservation and dissipation of energy, energy transfers, changes of state in the particle model, and internal energy and energy transfers. Do have a look out in the description as well because I'll try and put a link in there for some practice questions for you as well.
One of the most important things to do with energy is that energy can't be created, it can't be destroyed. It can only be moved from one place to another. It's one of the basic rules of the universe. Now, in this energy stores and systems topic, they might use the word system. System is really just a thing or things you're looking at. So, for example, a system could be a ball falling or a can full of gas. Okay, a closed system just means one where no energy or matter can enter or leave the system. Energy is only transferred between these stores. So these are stores of energy where energy can be held in it or it can be moved between these. So thermal energy is like heat energy, kinetic energy, also known as movement energy, gravitational potential energy, that's energy due to the height above the ground, elastic potential energy, the energy inside springs and elastic stretchy things, chemical energy, things like petrol, foods, inside glucose. Okay, magnetic energy, that of magnets, electrostatic, so that would be the energy in electricity or stored in an electric field. Nuclear energy, that energy inside an atom. Okay, so those are the 8 different types you need to know about, and energy can transfer between those types. So energy can be transferred by heating, or we can say that energy can be transferred by doing work. Now when we talk about doing work, that means the same as the energy transferred. So we've got a kettle is transferring heat energy, so there'll be some electrical energy arriving in the wire. That electrical energy will be transferred into heat energy in the filament, and that heat energy will go into the water. So that's how energy can be transferred there. And the number of joules of energy, of electrical energy, will be transferred into the number of joules into the water. But also there'll be a little bit of sound as well that comes out as wasted energy. So here are some examples of how we can do work to transfer energy. Well, when we throw a ball upwards, there is chemical energy inside his arm, and that chemical energy inside his arm will be transferred into the kinetic energy of the ball as he throws it upwards. As the ball starts to fall back down again, gravitational potential energy in the ball will be transferred into kinetic energy as it falls. A speeding car, which is hot on the brakes there, as you can see with our the red glowing brake pads there. Well, when we look at that, we can see down here that that's glowing red because we're transferring kinetic energy into thermal energy that's inside the tyres there. And when we crash a car, we're transferring the kinetic energy, transferring that into kinetic energy to make the crumple zones crumple. So that moving metal as it crumples, that's changing the speed into transferring that energy into the crumple zones and down here. Okay, so conservation of power then. Conservation of power is the rate of doing work. So the rate of transferring energy, how quickly I'm using energy or transferring energy. So two equations for this. We've got power equals energy divided by time, or power equals work divided by time. Remember that power and work done and energy transferred are the same things. Okay, so our two equations then, look, they've even got the same units, just to prove that they are the same thing. Okay, so there's something you need to know with power. You need to be able to describe how two machines with the same machine rather with two different powers, how it will do its job differently. Now we can say that both of these hairdryers will be able to do the same amount of work. They can both transfer the same amount of energy. They'll both dry the hair up eventually. But one's got a higher power rating than the other. That'll be this lucky lady here. And the one with a higher power rating is going to dry her hair more quickly. It's going to transfer the same amount of work to dry the hair, but it's going to do it more quickly because it's got a bigger power. And the reason for that is that we're dividing our energy transferred by time. So the shorter the time, the bigger the power. Okay, the shorter the time, the bigger the power. Okay, so kinetic energy and potential energy. So kinetic energy, we all know that that's movement energy. Well, there's an equation you need for that. So kinetic energy, measured in joules, is equal to half, or 0.5, times mass times velocity squared. Okay, so that's velocity times by velocity. Okay. Now, gravitational potential energy, so the energy due to the height above the ground, is potential energy equals mass times gravity times height. Now the unit for these then are down here. We've got gravitational potential energy in joules, mass measured in kilos, gravity field strength in newtons per kilo. You'll be given that in the exam. You don't need to recall that number. And the height as well. Okay, so for example, we've got someone jumping off of a cliff. They have gravitational potential energy stored in them at the top because of their height up here. And this will transfer, as they fall, this will transfer into the kinetic energy. The further down they fall, the faster, the higher the kinetic energy, until they land very safely at the bottom there, I hope. So definition of specific heat capacity. The specific heat capacity of a material decides how much energy it takes to increase the temperature of a kilo of that material by 1 degree Celsius. So the equation for this is the energy required is found by the mass of that object, as we said the mass is involved, times by the specific heat capacity, times by the change in temperature. Okay, and here are our units. So energy in joules, mass in kilos, specific heat capacity, joules per kilogram degree Celsius, and this theta thing up here, that egg-shaped thing, is the temperature change, okay, in degrees Celsius. Okay, so energy cannot be created or destroyed. It can only be transferred from one place to another. So this means that the total energy I put into a system has to come out as either useful energy or some wasted energy. So the total energy I put into my TV is the same as the total energy that comes out. And we've got to include there our wasted energy as well. So not only will light and sound be coming out of the TV, which is really useful, out the speakers and the screen, but there will also be some wasted heat energy that comes out normally out of the back. And you can feel that if you put your hand down the back of electrics, you can feel that they are generally warm. Now, not only is the total energy equal to the total energy out, we can also think of this in a closed system. So all I mean by that is like a room where the door is and the windows are shut. So when a hot pie, you take it out of the oven of one room and you put it into a cool room, well, what's going to happen there? The energy that's stored in the pie, in the thermal store of the pie, that energy store is going to go down. And it's going to transfer that energy into the energy store of the room, which is going to go up. So the room is going to warm up just a little bit, the pie is going to cool down quite a lot. And the total energy of both, when you include both of them in, the total energy stays the same. Okay, conduction and convection. So what is conduction then? Well, when I heat up, for example, maybe at the end of a metal rod, you can imagine these as the particles of that metal rod. As I give them more heat to start off with, only the very nearby particles are vibrating more, but gradually every particle next to that will start to vibrate more as they collide into each other. They're going to bump into each other and pass on this kinetic energy until eventually the whole rod would end up being heated and warmed. Okay, convection currents are the movement of warm fluids. So that could be gases or liquids. They can both have convection currents in, where your air particles rise up because they're less dense and sink back down because they become more dense once they've cooled down. Okay, so convection is moving air particles. Conduction is the vibrating particles of a solid, and conduction happens best in solids because they're close together. Okay, houses have got insulation to stop these two methods of heat transfer. Now, air is a poor conductor, so having air trapped in a foam in a gap between an outer wall and an inner wall reduces heat loss. And this is called cavity wall insulation. So that's putting foam or polystyrene beads in a gap between an outer wall and an inner wall. Loft insulation, that's going to stop convection currents forming in the loft because you've got a layer of nice thick trapped air just above your ceiling. Double glazing has got a vacuum layer. Now, a vacuum is really important. You know that that's got no particles in it. So a vacuum, we're not talking about a vacuum cleaner. We're talking about a vacuum like you find in the emptiness of space. So that's going to stop both conduction and convection. And people often forget about these. So draft excluders is the thing, the little doggy-shaped thing that your gran has got at the bottom of her door to stop the drafts. Okay, efficiency. So there are two equations, two different ways of working out efficiency. There is working it out as a decimal, and there's working it out as a percentage. So if it's a decimal, it's going to be a number between 0 and 1. Okay, 1 being really efficient, 0 being awful, no efficiency whatsoever. And then as a percentage, you're going to have a number between 0 to 100%. Okay, now we can talk about efficiency either in terms of energy, so useful energy out of a TV over the total energy you put into a TV gives you the efficiency, or we can think of it as power. So the useful power out of my Hoover divided by the total power I put into my Hoover. Very interesting. Okay, the useful energy out will hardly ever be the same as the total energy in, because energy is nearly always wasted. So for example, friction of moving parts, unwanted sound or light given off. And most wasted energy is lost as heat to the surroundings. So most pieces of equipment end up warming up the air around it, and that eventually will just be dissipated and will just be spread out into the surroundings. Okay, so how do we reduce unwanted energy transfers then? So energy transfer is basically wasting energy. How do we reduce that? So this basically means that we're wasting less energy. Okay, well, if it's got moving parts, put some oil on it. So lubricants, they reduce the friction on moving parts, meaning less energy is going to be wasted as heat. Because of course friction causes heat, like rubbing things together causes heat. So how else can we reduce unwanted energy transfers? We can put insulation around a boiler. We could maybe make our kettle have a silver inside so that it reflects heat radiation back into the kettle, meaning more heat will get transferred into the water. So insulation, for example, foam, wool, shiny silver, fiberglass, they're all going to reduce heat loss, and that means that less energy will be wasted as heat. So very useful. Okay, so how to calculate the power of appliances then? A lot of equations on this slide, but in a nutshell, what have we got here? So potential difference, voltage, is the energy transferred by charges. So energy is the charge times the voltage, and voltage is the energy transferred per charge. Okay, same equation, just rearranged. So energy is measured in joules, charge in coulombs, voltage in volts. So there are three different ways of calculating power for electrical appliances. We've got power equals energy divided by time that we've seen before. Power equals I squared R, so current squared times resistance. And we've got power equals current times voltage. So P equals IV, P equals I squared R, P equals E over T, or P equals W over T. So the national grid then, this is our electricity distribution network. So the national grid is made up of these parts. It's made up of a step-up transformer, it's made of our cables, and it's made of our step-down transformer. So the step-up transformer, the job of that is to increase the voltage to reduce energy loss in the cables as heat. So it reduces energy lost as heat. The step-down transformer, just before the house, before our homes, that reduces the voltage back to safe levels for households. So step up increases the voltage to reduce heat loss. Step down reduces the voltage to make it safe again. The particle model. So what do we know about the particles in a solid, in a liquid and in a gas? So what can we say about the energy of the particles? Well, as they go from solid to gas, so we can imagine this as maybe water. We've got our ice and we've got our normal water. We've got our steam up here. And check out my handwriting. Yes, it's like a toddler. So there is my steam. Okay, so we've got our ice all the way up to steam. Energy of the particle goes up as we go from solid to gas. The arrangement then, so here they are all touching. Liquids, they are partially touching. Gases, they are not touching. They're far apart from each other. What about the forces of attraction then? Well, solids, they have strong forces of attraction. That's why they are so close together. Gases, really weak forces of attraction. In fact, they've broken their forces of attraction. That's why they're not touching each other, they're not connected. And the distance between the particles, that also goes up. And the shape of them, so these ones will, will sit at the bottom of a container. Liquids will fill the entirety of the bottom of a container, and gas will fill up the whole of a container. Density then, what is density? Density is basically how much mass is packed into a volume. The more mass you pack into a volume, the bigger that number is, the bigger the density. Okay, the smaller your volume, the smaller that is, the bigger the density. So you put mass into a smaller volume, you've got a bigger density. And that is rho, that's the unit, the symbol there for density. Rho equals mass divided by volume. Mass in kilograms, volume, meters cubed. Okay, giving us our density in kilogram per meters cubed. So we can calculate the volume of a regular object like a cuboid by doing width times length times height. We can find the volume of a liquid really easily. We put it into a measuring cylinder, and 1 milliliter on our measuring cylinder is the same as 1 centimeter cubed. So that gives us our volume really easily. Now, if we want to take find the density of an odd-shaped object like a Lego man, so for each of these equations, whether we're doing the cuboid, a liquid, or the Lego man, we need to be weighing them on a set of scales first to find their mass. So we just basically need to find these things in the equation. So we can calculate our volume by doing width times length times height, or from a measuring cylinder, or by dipping our Lego man into our Eureka can here. And when you put the Lego man into the water, he will shift an even volume of water, an equal volume of water to his volume. So out will come water, and we can collect that in a measuring cylinder. So that water goes into here, and that will tell us the volume. So internal energy in changes of state then. What is internal energy? It's the combination of the particle's kinetic energy and its potential energy due to their position or their state of matter. So when you heat something up, the temperature changes. And the temperature change depends on the mass of it, the mass of the object, the material, the specific heat capacity, for example, and the amount of energy you put in. So when we heat something up, the mass of it and the material of it will decide the temperature change. So we can see our changes of state here. We've got melting when it goes from solid to liquid. We've got evaporating when it goes from liquid to gas. When it goes back again, we've got condensation. And up here we've got liquid into freezing liquid into solid is called freezing. Now we can have particles skip out the liquid phase, and we call that sublimation. And we can also have a gas go straight back into a solid again, and we call that sublimation. Okay, they've both got the same name. We can see there the different states of matter as we go through the changes of state. So we can see also that our particle speed increases as we give it energy. Okay, so latent heat then. What is latent heat? Well, if we have a look at this graph over here, this is a graph of showing our temperature against the time that we're heating something up for. So this is basically the amount of heat provided going that way. So when something's a solid, we provide heat, the temperature goes up. When it starts to melt, when it hits its melting point, we're still giving it heat, but its temperature staying the same. With our liquid state, we're giving it heat energy again, so its temperature is going up. And then when it's changing state, the temperature stops changing until it has all changed state, and then the temperature can keep going up again. Now these flat parts here, these flat parts is where energy is being supplied to change the state. So the energy is being supplied to change the solid into a liquid. The temperature is not changing in that point, but it is changing state. And the same up here. Energy is still being provided, but it's not changing state. The temperature is staying the same. So the specific latent heat, when we look at this equation over here, the specific latent heat is the energy needed to change the state. It's the energy of the flat bit of the graph. Okay, so the energy required there to change the state is found by the mass of that object, the mass of that liquid or gas, times by the property of the liquid of the specific latent heat. So just like specific heat capacity, each material has got a unique number that helps us work out how much energy it takes to change the state of it.